This is Octave, and I've loaded the demo script that uses basic Octave functionality and also the Beckhoff helper functions. We now first run the section with a filter definition, setting the desired sample rate and filter order. And we see the first coefficients that have been calculated by the remess function. So the remess function is returning the B coefficients for the FRR filter. So the next step is to use the calc ripple function in here and also plot some frequency and step responses. The first result looks like this. We have a passband, stop band. You see here a passband up to 1 kilohertz and then transition band down to 2 kilohertz, and this is a beginning of the stop band. The related step response, the unit step here at t equals 0, and the filter response also shown here. Looks quite good, but in the first region we have a ripple that could be better, could be optimized. So we will now apply a weighing function. So we add a weight of factor of 10 to the passband definition and leave the stop band to 1. And just doing the same again, we calculate new B coefficients using the remess function, calculate the ripple, and also plot the responses. We are now getting to new graphs. And if we take a look on the transfer function, this looks way better in the passband definition. So this is a new one, and this is the initial design. We take this design, this is okay from my perspective, and scale this to 1 so that we have a transfer function that is actually scaled to 1 and not like this as we have here. So it's an amplitude difference, and we want to have this scaled to 1. Next script does also this, and we will review the filter here. You see that it's perfectly matching 100% gain in the time relation. So the filter is designed. We have just used scale gain and quantizer functions. So everything in Octave is prepared to be sent to TwinCAT, and this is done using the XML export function. So it defines on which channel which filter has to be used, the type of filter, and also the type of ELM terminal. Just give it a file name, and we will soon see the this working directory. We will just see the transfer function. Updated one here, myfilter.xml, and this file will now be transferred to the CX. I'm using TeamViewer here to connect with the system, and that's why I'm checking this to be transferred to the system. In TwinCAT, I'm actually on my terminal, and on this terminal, this is a ELM 3604, a 4-channel IPE in voltage mode, and operating at full data speed of oversampling factor of 20. So that means with a cycle time of 1 milliseconds, we end up with a 20 kilosamples per second sample rate. To use the filter design, we are now turning to the startup list, and startup list is configured to set the voltage measurement and decimation factor of 1, so full speed to the PDO. And now we import an XML description. Just select this filter file that we've created, and we don't want to overwrite anything here. And this is a filter definition, so user-defined FRR filter with the filter coefficients, and we'll now activate this configuration. And as long as it's still running, we will see review step response and find an interesting point and frequency, for example, the minus 3 dB point, and the minus 3 dB is roughly at 1455 Hertz. So we will stick to this frequency and see if we get a 70% ratio between output and input. This system is set to this specific frequency, the minus 3 dB frequency. And on my terminal, this is my terminal, I've checked two channels, channel 1 and channel 2 in the scope. And we see here that if we run the scoping, that we have a relation between roughly 100% and 70%. We can check the behavior if we just activate or deactivate filter 1. We do this online, and we'll then go to the second channel and set the actual filter, which is now set to user defined, to 0, no filtering, and immediately the channel 2 also goes up to the full value because it's not filtered. And as soon as I step back, of course, the output will drop to the 70%, and we can also do more checks on this.